Hello everyone, welcome to our presentation. I'm Liu Jiakun from Zhejiang University. Today I will talk about the technical debt, shortened as TD, in deep learning frameworks. To answer that, is using deep learning frameworks free? The collaborators of this paper are Huang Qiao and Li Shanping from Zhejiang University, Xia Xin from Monash University, Imad Shihab from Concordia University, and David Low from Singapore Management University. Nowadays, deep learning are widely applied in a range of life-impacting software, from the car driving to risk management. To develop these applications, developers often employ deep learning frameworks. Deep learning frameworks can provide interfaces to deep learning applications, for example, the control flow and the data transfer between tasks, specific algorithms. By using these deep learning frameworks, application developers do not need to care about the concrete implementation and pay more attention to their application development. However, the field of deep learning is still rapidly growing due to time pressure, market competition, and cost reduction. Framework developers often leave technical debt in their frameworks. Previous research found that TD is detrimental and can increase the cost. However, it is still unclear whether there is TD in deep learning frameworks and what are these TDs. Therefore, we employ the self-admitted technical debt, shortened as SATD, as an indicator of TD. Such TD is a comment that is intentionally introduced by developers to alert the workaround of the solution. For example, in TensorFlow, a comment saying to do identify when this infrequently causes timeouts indicates that the corresponding code is problematic and need further investigation. Framework developers are aware of such TD, but application developers may not be. This practice may cause application developers to be negatively impacted or limit their capabilities. We include 7 deep learning frameworks, namely TensorFlow, Keras, Caffe, PyTorch, MXNet, CNTK, and Deep Learning 4J. We extract a total of 200,000 comments from these frameworks. We perform 3 iterations of card-starting approaches to identify and manually label the categories of these comments. With this data, we first explore that is TD prevalent in deep learning frameworks? The answer is yes. There are a total of 7,000 comments that indicates TD, which correspond to 2% of all comments. At any granularity, for example, file level, class level, method level, and comment level, TensorFlow has the largest number of TD, Keras has the smallest number of TD, CNTK has the largest proportion of TD, and MXNet has a small proportion of TD. This result reveals that TD is common in deep learning frameworks, especially in TensorFlow and CNTK. We observe that there are 7 types of TD in deep learning frameworks. Compared with developers in non-deep learning projects, frameworks in deep learning frameworks are confronted with new challenges. We observe the algorithm debt and the capability debt, which is not identified in previous work. We first talk about design debt. Design debt indicates that the design of code is suboptimal. In the first example, the design details of the framework have not been determined yet when the code is implemented. One possible reason is the fierce market competition, and the developers rush to implement related functions before the design decisions are made. Defect debt refers to the code that behaves in an indented ways. In the first example, the bug is triggered in certain cases. By reading the code related to this TD, we observe that this TD can be related to the use of widely adopted probability and statistics-based algorithms, which are sensitive to the input data. These algorithms lead to the defects of deep learning frameworks difficult to reproduce. When application developers use these flawed frameworks and trigger these bugs, defect debt can cause unexpected results in their applications. Another TD is documentation debt. Documentation debt indicates missing, incomplete documentation. The second example shows that one of the reasons of documentation debt is that some framework developers expect other developers to provide a clear description of the code. Documentation debt can lead to the framework developers not fully understand collaborators' work and can increase the difficulties for the maintenance. Requirement debt indicates the incompleteness of the method class at a particular time. The first example shows that a new requirement, the Bidirectional STM, are identified during the development of existing requirements, but CNTK refused to implement it yet. When application developers want to use this technology in their applications, they found that this technology is not implemented by the deep learning frameworks. Thus, application developers have to implement this technique by themselves. We also observe the test debt. In the second example shows that there is dead test case in deep learning frameworks. This can lead the static analysis tool to be unable to find abandoned code. We also observe the compatibility debt. This indicates that developers admit the deep learning frameworks bind themselves too tight with other open source packages. If the deep learning framework developers use too many dependencies, they are also exposed to the risk brought by these dependencies. Algorithm debt can pull down the performance of the systems. It is often the case that the computation task of deep learning frameworks is quite often heavy, and for such cases, the suboptimal implementation of the algorithm can have an adverse impact. As a result, we find that in most projects except Keras, design debt is the most common debt. And following that, for most projects, either requirement debt or algorithm debt takes the second place. In Keras and Café, compatibility debt accounts for more than 10%. Keras do not implement code that handles low-level operations such as tensor products, convolutions, and so on. Instead, it relies on external libraries such as Theano. Hence, Keras enjoys the convenience provided by the backend projects at the cost of the maintenance of the dependencies. We compare the technical debt in deep learning frameworks with non-deep learning projects. We found that SATD is more common in deep learning frameworks compared to the non-deep learning projects. There are also new categories of technical debt, for example, the algorithm debt and compatibility debt in deep learning frameworks. The implications of this paper are that, for example, if the deep learning applications need to use the out-of-box implementation of the cutting-edge deep learning algorithms provided by the deep learning frameworks, we suggest the application developers not to use the frameworks with more requirement debt, such as deep learning 4J, where many algorithms remain unimplemented. For researchers in deep learning, we suggest deep learning researchers try to test their algorithms based on more deep learning frameworks rather than only based on the interfaces provided by one deep learning framework. In summary, we manually label 200,000 comments. We find that TD is common in deep learning frameworks. We observe that there are 7 types of TD in deep learning frameworks, and design debt is the most common TD, followed by requirement debt and algorithm debt. Thank you.